lenses and how they behave. I went ahead and I've created my diagram here. This lens, this wall is not really coming in all that great, but that's all right. I'm not divergent lenses, I'm meant to be divergent mirrors. And I have my focal point out here. Well, remember that the focal point is actually out here. It's inside the material when talking about divergent lenses. So I'm going to ray trace again. I'm going to come up with a new equation and a new idea. So, boom, come up with one ray. It bounces off that ray. Okay, it's heading in parallel, so we pretend that it comes from this focal point. It comes back out like that. Okay? So there's our first ray in our ray diagram. Our second ray is going to head straight for the focal point. I'm going to draw that in. There we go. Heading straight for the focal point. It's going to hit that surface, and it's going to bounce out, but it's going to bounce straight out. Okay? So I have one that comes in, strikes, and then bounces straight out. The last ray we're going to draw, and I wish my board would dry a little faster. Okay? It's going to come from this point. It's going to strike the dead center. Okay? And then it's going to bounce out again. Cool? So what we're going to do is we're going to retrace some of these rays. So here is the virtual part of that ray. That ray looks like it's come from that point straight out. Okay? This ray strikes and bounces out, so it appears that it's coming right there. And then this last one, if we follow it back, hits that point right there. So we've got ourselves another point where I'm creating an image. But what's the difference? Wow, this is interesting. So over here, I have it right side up. Over here, I have it right side up. When we did it with convex or concave, we had an image here, and it was flipped over here. Okay? And now I have an image here, and it's right side up. Cool? Well, it turns out it has the exact same equation. It represents, okay, my image. This represents my object. And this represents my focal length. So to the surface of the mirror to the object is the object distance. The surface of the mirror to the appear of the image is my image distance. And the surface of the mirror to the point where all those parallel rays will converge is my focal length. Now, I guess the first question I should ask you before going any further is this object, is this image, I should say, not object, is it real? Well, the answer is no. It's not real. It's not real lines that convert at that point. It's these imaginary lines that convert at that point. So it's an imaginary image. It's virtual, is what we call it. It's not a real image. Okay? So it turns out that we have the exact same equation. We have 1 over object equals 1 over focal. For that exact shift that we the previous images. And we also have this relationship. We have the magnification. Okay? And it still has that negative sign. So, because it still has this negative sign, you should be able to justify one of these terms, either the object distance or the image distance, as a negative distance. Okay? One of those should be negative. Well, if we took this to be real image, this is a real distance, with real lines going over there, then it would say that this is real. And this is an imaginary distance, or what we're going to treat as a negative distance. Okay, so this value is going to turn negative. So I'm going to have a negative over a positive times up with identification. Now, it could be 1/2, and it would still reduce my size if this is 2 centimeters to 1 centimeter. But because it's turned positive, it's going to be a real image. It's going to, or not a real image, sorry. Because it's going to be positive, it's going to be right side up. It's not going to be inverted. It's going to be the right side up. Okay? Cool? So that's a convex mirror. And it's following the exact same behavior. One over object per image, one point. And in this case, you've got to remember that this image is materializing inside the mirror. Okay? Cool? That's mirrors.